Good afternoon, everyone. I'm Sanjukta Roy. I'm from Raman Research Institute, Bangalore. Today I want to take you to the very exciting world of quantum science and technology with ultra cold atoms. So the outline of my talk is, first I'll give you an introduction to ultra cold atoms and Bose-Einstein condensate. Then I'll talk about how we realize Bose-Einstein condensate in a laboratory. Then I'll talk about the exotic phases of matter via Bose-Einstein condensate. For example, superfluidity and supersolidity. Then I'll talk about quantum technology with ultra-cold atoms. And then I'll give you some glimpse of the ultra-cold atom experiments on Rydberg atoms at Raman Research Institute. So any talk on Bose-Einstein condensate cannot begin without paying tribute to Satyendranath Bose and Albert Einstein. And you may notice that this year it's very special because it's the 100 years of the prediction of Bose-Einstein condensation or the discovery of Bose-Einstein statistics by Satyendranath Bose and Albert Einstein. So and the young generation should know that we have in Indian science a very glorious past which actually gave birth to the quantum mechanics which which was the root of great advances in the last century. So Satyendranath Bose had worked out a new statistics for photon and wrote an article, Planck's law and the hypothesis of light quanta, and sent it to Albert Einstein. And Einstein had adapted this seminal work by Bose to apply it to other bosonic particles and atoms, and thereafter predicted the phenomena of Bose-Einstein condensation. So the Bose-Einstein condensation was first observed in strongly interacting system in 1938 in superfluid helium, but in weakly interacting system only much later in 1995, and I'll tell you why in the next few slides. So it has the discovery of Bose statistics has a very interesting story. So Satyendranath Bose was teaching in Dhaka University. At that time, it was part of British India. And while teaching Maxwell-Boltzmann distribution, he found that it cannot explain the physics of microscopic particles. He realized that for microscopic particles, you cannot definitely talk about or pinpoint the position and momentum of these microscopic particles. So you can only talk about the probability of having these microscopic particles in a phase space of volume h cube. So this he wrote up in this article. So the main point of this article, which you will see that which Bose had written in the letter accompanied, he had written to Albert Einstein. He wrote, you will see that I have tried to deduce the coefficient 8 pi mu square by c cube in Planck's law independent of classical electrodynamics, only assuming that the ultimate elementary regions in the phase space has the content h cube. I do not know sufficient German to translate the paper. So he requested Albert Einstein to translate the paper in German and get it published in the journal which was in German. And he also wrote that he was the one who had translated Einstein's paper on general relativity to English, and so he wanted to, imply probably it would be nice if you return the favor. So Einstein translated the seminal paper in German and got it published under Bose's name in 1924. And this year is the 100 years of that great seminal paper. And Einstein replied to Bose saying, "It is a beautiful step forward." And thus a new Bose-Einstein statistics was born. Einstein recognized the importance of Bose's seminal paper and generalized his new statistical technique to particles with integer spin and predicted the phenomena of Bose-Einstein condensation. So we know that all the particles can be categorized into two groups, bosons and fermions. So bosons can, any number of bosons can occupy any of this quantum state. But fermions, as we know, one fermion can occupy only one quantum state, and one fermion fills the quantum states up to the Fermi energy, and when it fills up to the Fermi energy, we get a Fermi degenerate gas. But when all the bosons are condensed to the lowest quantum state, we get what is called a Bose-Einstein condensate. So what is the prediction of Bose-Einstein condensation? The lowest energy state can be occupied by a large number of particles well above the absolute zero temperature. When the temperature is very low, the bosonic particles will gather together at the lowest quantum state even without any attractive interaction. And this is called the Bose-Einstein condensation. So all the particles occupy the same quantum mechanical state. They are all in phase and they are all phase coherent. So this is a simplified picture of a Bose-Einstein condensation. So at very high temperature, for example, at room temperatures, the particles are moving like billiard balls and with velocity v. Now, as you lower the temperature, the de Broglie wavelength, which is inversely proportional to the square root of temperature, that becomes larger and larger. And as you go down in temperature, at some point, the de Broglie wavelengths start to overlap, and there it reaches the critical temperature for Bose-Einstein condensation. And at temperatures very close to absolute zero temperature, you get a pure Bose-Einstein condensate, which you can also call a giant matter wave. So the phenomena of Bose-Einstein condensation can be understood from this video. You see here the particles are like balls as you lower the temperature, and particles are trying to accumulate to lower and lower quantum states. And see their de Broglie wavelengths increases as the temperature decreases, and the waves become larger and larger and becomes equal to the average distance between the two atoms. And at very, very low energy, all the bosons are at the same energy in the same quantum state, and this is a giant collective quantum wave called a Bose-Einstein condensate. So how cold is the temperature where we get the Bose-Einstein condensate? Now here is the temperature scale. This is the sun, and at 0 degrees, so freezing water, and liquid nitrogen is already very cold at 77 Kelvin, and helium is at 4 Kelvin here, and we have all heard about cosmic microwave background at 2.7 Kelvin, which is here. And so for Bose-Einstein condensate, we go down and down in temperature using laser cooling. I'm going to explain it in a few slides, then evaporative cooling. And down here at nanokelvin, and even the record is like a few tenths of picokelvin, we get Bose-Einstein condensate, which is the coldest matter in the universe. So as an experimentalist, I would like to teach you how do we realize a Bose-Einstein condensate in a laboratory. So we need to know what is the condition which we need to satisfy to get a Bose-Einstein condensate. Now the condition which we get, which is like the overlapping of this de Broglie wavelength, this gives the condition that the product of the density and the cube of the de Broglie wavelength should be of the order of 1, or more precisely this number 2.612. Now n is the atom number density, and de Broglie wavelength, as I had explained, is inversely proportional to the square root of temperature. Now this practically comes to the de Broglie wavelength of around 300 nanometer, and which gives us a temperature roughly around 300 nanokelvin and an atom number density of around 10 to the power 14 atoms per centimeter cube. So from this slide, what I want to explain is that it's not a one-step process. There are several steps which is involved in this. And so here, the first step is to have the phase space density low from the room temperature to 10 minus 6, and then 10 minus 3, and then we have so it's like a 3, 4 steps till we go to the condition which is satisfying for Bose-Einstein condensate. So for laser cooling and trapping, we cool down from room temperature to around 100 microkelvin temperature. So how do we cool down? So this works on radiation pressure. You have all heard, seen comets. So you have seen that the tail of the comet is facing away from the sun because of the radiation pressure of the sun. That means the radiation, photons from the sun has enough force that it can make the tail point away from the sun. So this is the same principle. So what we do is we use Doppler cooling. So to understand the Doppler cooling, let's think about an atom with a ground state and excited state, and laser having frequency nu with energy which is exactly having energy with, exactly equal to the difference between ground and the excited state. And if we scan the frequency of this laser, you can excite the atom from the ground state to the excited state. Now, what happens if the atom is moving towards the light beam? Suppose you have a laser light and you have the atoms moving towards it. Now, the atom will see, because of the Doppler shift, it will see the frequency upshifted. Now, the opposite happens when the atom is moving away from the laser beam. It will see the frequency downshifted. Now, so this is the principle of the Doppler shift or the Doppler effect, which we use for laser cooling to cool down atoms from room temperature to microkelvin temperatures, which is the first step in the process to go towards Bose-Einstein condensate. So suppose you have a laser beam and the atom moving towards the laser beam. Now, the laser beam is already red detuned from resonance. That means the frequency is already less than the atomic transition frequency. So here, the laser beam frequency is somewhere here, not this full, not the frequency for the transition from the ground state to the excited state. Now, when the atom is moving towards the laser beam, it sees the frequency upshifted and hence sees it on resonance and hence absorb a photon. Oops, sorry. Okay, it absorbs a photon and gets a momentum kick opposite to its direction of motion. and hence as it absorbs the photon, the atom gets slowed down. Now as soon as it is absorbed, it has a spontaneous emission, but that spontaneous emission happens in random direction. So in 1 second, there is 10 to the power 6 absorption and spontaneous emission. So after so many cycles of absorption and spontaneous emission, the net effect of absorption slows down the atom, but the effect of the spontaneous emission averages out to be 0. So on an average, the atom gets slowed down. So you can see there is a strong interplay between the dynamics of internal and external degrees of freedom, which leads to cooling of atoms. So what happens if you have laser beam from both direction? So whichever direction the atom tries to move, it gets slowed down. Now you see here that the force is always opposite to the direction of velocity. Now at slow enough velocity, the force is linearly proportional to the velocity. So it's like a damping force, a friction damping, which slows down or cools down the atom. Now what happens if we do it in 3 dimension, because we want to cool down the atoms in all 3 dimension? So this is called what is called an optical molasses. It's like a ball in a very viscous sugary syrup. And there the ball gets slowed down because of the viscous force of this liquid. And here's the real picture of this optical molasses. An atom feels that viscous force within the laser beam. But this is only cooling. There is no trapping. We want to actually trap those atoms and position it in a point in space so that we can do experiments on them. So how to do that? To do the trapping, we need a position dependent force. So for that, we use magnetic field, which is position dependent. So we use 2 magnetic coils with currents in the opposite direction, which produces a 0 at the center, and it increases linearly in all direction. So as the atoms try to move away from the center, it comes more on resonance and feels a larger force which pushes it towards the center. So whichever direction it tries to do move, it gets more force which pushes it towards the center. So it's like a restoring force in a spring. The more you take it out of the center, more force you feel it, which pushes it towards the center. So this leads to the trapping of atoms. So this is the configuration of what is called a magneto-optical trap. So here the force is proportional to the distance from the center, which leads to trapping. So here we have trapping and cooling all together. So this is parameters for the magneto-optical trap. So these are the density, it's around 10 to the power 9 to 10 to the power 11 atoms per centimeter cube, and we can get temperatures of 100 microkelvin, and we can get sizes of around 1 millimeter. But please note that it's still dilute atomic gas. That means the interatomic separation is much larger than the size of the atom. It's much dilute than in liquid or in a solid state. But the striking thing you should note is that at typical velocity of atoms at room temperature is like 30,000 centimeters per second, but from that in a magneto-optical trap, it's slowed down to few centimeters per second. So this is a typical picture of a magneto-optical trap. So this is a picture of a magneto-optical of real atoms in a in a vacuum chamber, which is also called MOT. So these are cold atoms at 100 microkelvin temperature. You can see it glowing inside the vacuum chamber. So it has to be kept inside the vacuum chamber, otherwise the hot atoms can knock down the cold atoms from the trap. So the vacuum which is maintained inside this chamber is like 100 billion times less than the atmospheric pressure. So for discovering the techniques for laser cooling and trapping, Stephen Chu, Claude Cohen-Tanouji, and William Phillips were awarded the Nobel Prize in 1997 for development of methods to cool and trap atoms with laser light. Now you may be wondering, how do we know what is the temperature of the atoms? Now, as I had told that the velocity of the atoms depends on the temperature. So it goes as square root of temperature. So to measure the temperature, we just release the trap and let the atom expand due to its temperature. So as it expands, we record the size at different expansion times. And from that, we measured that how fast it has expanded in a particular time interval. From that, we get the temperature of the atoms. Now, isn't it already enough for go to Bose-Einstein condensate? Actually not, because there is a fundamental limitation. That means, as I had said, you are absorbing a single photon. But absorbing a single photon heats up the atom by around 1 microkelvin temperature. So we cannot go lower temperature than that. So to go further down in temperature, we have to adopt a special technique called evaporative cooling. So which can take us to nanokelvin temperatures, where we can get the BC transition temperature. So we have to resort to traps which has no photons in them. So there are no absorption of photons to heat up the atoms. So we need to have dark traps where there is absence of resonant light and do the evaporative cooling. So there are two options: magnetic trap or optical dipole trap. Now, optical dipole trap, we have a laser beam which is far away from resonance, and we focus the laser beam and it creates an optical potential where we can trap the atoms. And so here the intensity should be very high for the laser beam, and it should be as away from resonance as possible. So here you can see atoms trapped in an optical dipole trap, and atoms which are not trapped in the dipole trap are falling away. So these are atoms which are trapped in a crossed optical dipole trap. Another way to trap the atoms is magnetic traps. We have coils with current in opposite direction, where we create a potential where atoms can be trapped with zero of the magnetic field, and the magnetic field increases linearly in all direction. So this has the same principle as you can see a small magnet, a rotating magnet which is levitating on a very strong magnet. So this is the same principle in which the magnetic trap works. So the next step, which is very crucial, is what is called evaporative cooling. That means we lowered so we have the atoms in the trap, and then we slowly lowered the trap depth. That means the depth of the potential, and the hotter atoms which are at the outside or the periphery of the trap, they go out of the trap. And the remaining atom, they undergo elastic collision among themselves, and overall temperature reduces because the higher energy atoms have gone out of the trap. And in this way, the the temperature eventually cools down, and all the atoms finally accumulate in the lowest quantum state, and we get a Bose-Einstein condensate. So this is like cooling in your coffee cup. The hotter molecules, they evaporate, and then the remaining molecules, they cool down, and your coffee becomes colder. So that's why it gets the name evaporative cooling. So how to recognize whether we have got a Bose-Einstein condensate? So for that, we need to look at the Gauss-Pitavsky equation. So it's actually a nonlinear Schrodinger equation. So you have a kinetic energy term and a potential energy term. And you have an interaction term, which is called the mean field interaction. So this happens because of the interatomic interaction in the Bose-Einstein condensate. So in the Thomas Fermi limit, that means the kinetic energy, if we put it to 0, because in the Bose-Einstein condensate, the temperature is very low in the nanokelvin temperature. So we can safely ignore the kinetic energy. So the atomic density profile becomes like an inverted parabola. So this is the shape what we get when we have a Bose-Einstein condensate. This is because of the mean field interaction in the Bose-Einstein condensate. And in the non-interacting case, it's like this shape. So this interaction in Bose-Einstein condensate gives it a inverted parabola kind of shape. And this gives the BC phase transition temperature. So what is the signature of a Bose-Einstein condensate? So in a uniform gas, the Bose-Einstein condensation happens only in momentum space. But when the Bose-Einstein condensate is trapped, you have a special signature, which is very convenient for experimentalists to recognize Bose-Einstein condensate, is that it happens in position space as well. So the onset of BC occurs at the transition temperature, and it's observed as a sharp peak in the density profile emerging in the center of the trap, resulting in a bimodal profile. So you will have a broad thermal profile and a very sharp profile for the condensate. So this is actually the real signature of the onset of Bose-Einstein condensate in our experiment, which I had did during my PhD at TIFR Mumbai. So here you could see, can see a sharp peak due to the Bose-Einstein condensate and a broad thermal background. And you can see this highly dense feature at the center, which is the signature of Bose-Einstein condensate. So this is like a signature which helps us recognize the Bose-Einstein condensate. So you can see before the BC phase transition, you have a broad thermal profile. And at the transition temperature, you have a coexistence of the broad thermal profile and the sharp peak of BC. And at very low temperatures, you have a pure Bose-Einstein condensate. So here's the formation of Bose-Einstein condensate. Okay. So the Nobel Prize in 2001 was awarded to Eric Cornell, Wolfgang Ketterle, and Carl Weimann for achieving for the realization of Bose-Einstein condensate in dilute gases of alkali atoms. So this picture actually shows the phase coherence in Bose-Einstein condensate. So it's like all the atoms in the Bose-Einstein condensate are phase coherent. It's like the soldiers marching in lockstep. And here you can see that all the atoms, it's like, atoms in the Bose-Einstein condensate, they're all phase coherent, they're all identical. And the atoms which are not, they are going out of the out of this BEC or out of the trap. So this is a signal from our Bose-Einstein condensation experiment at TIFR Mumbai. So here you can see a broad thermal profile at below the, above the BC transition temperature. And at the BC transition temperature, we see a coexistence of the thermal profile and the Bose-Einstein condensate. And at very low temperatures, much below the BC phase transition, we see a pure Bose-Einstein condensate. So this is the picture of the BC experiment. And here is where we had produced the Bose-Einstein condensate. So it looks very complicated. So it's not challenging to have each of the component working separately separately, but the real challenge is to have all the components working properly together at the same time. So this is the real challenge of realizing a Bose-Einstein condensate. So this is the 3D picture of the Bose-Einstein condensate, and this is the VC phase transition. So this happens to be the first Bose-Einstein condensate in India, and this was our humble tribute to Satyendranath Bose. So I had worked on another Bose-Einstein condensate experiment during my postdoc in Florence in Italy. So here it had an extra step which we called a sign cell where the Bose-Einstein condensate was produced. So here you can see this extra step which was done. Where the atoms were transferred to the sign cell, and there we used to produce the Bose-Einstein condensate. So here you can see above the transition temperature, you have a thermal cloud, and then you have the bimodal profile of BC and thermal gas, and then you have a pure Bose-Einstein condensate. So what is the specialty of Bose-Einstein condensate? So how does it distinguish from ordinary thermal atoms? So it's the same distinguishing feature of coherent laser light with incoherent LED light. For example, with laser light, you can form an interference pattern, but not with incoherent LED light. So this is the thermal cloud of atoms. And here you have, you can see the Bose-Einstein condensate. So what happens if we split the Bose-Einstein condensate into two parts and then recombine, what we'll get is an interference pattern, just the same way as you get from a laser light. So which is the evidence that Bose-Einstein condensate is a phase coherent form of matter. So another exotic feature of Bose-Einstein condensate is superfluidity. So what happens if you stir your coffee cup and you go out of the room, and when you come back, you still find that your coffee is still stirring. So it would happen only when you have superfluid in your coffee cup. So superfluid is a fluid with zero viscosity. So it's analogous to superconductors where the electric current flows without resistance below a critical temperature. So here you can see the superfluid transition in liquid helium. So superfluidity, which is the property of a substance sustaining persistent dissipationless flow, it was first observed in liquid helium by Kapitsa, John Allen, and Don Meissner in 1937, and they were awarded the Nobel Prize in 1978. So what is the specialty of superfluidity? So if you have a normal fluid in a bucket and you rotate it, you see a meniscus like this. But if you have a superfluid in a bucket and rotate it, you will see that it does not form a meniscus like this, but it will have velocities which are not continuous, but in steps. Because superfluid is a matter wave and it cannot take velocities continuously like in normal fluid, but since the matter wave has to close on itself, it can take velocities only in quantum steps. So if you rotate the superfluid, you can have what is called the quantum, the velocities can only increase in quantum steps. So which gives rise to what is called vortices. So this is what you get when you rotate a superfluid, what is called a vortices, the same way which you have in superconductors. So if you rotate a BC, which is a superfluid, the faster you rotate, the more vortices you get. So this is actually evidence of the superfluid property of Bose-Einstein condensate. So another exotic property of Bose-Einstein condensate, that it can also give rise to supersolidity, which is a very exotic form of matter, which is the coexistence of solid and solid-like behavior and superfluid at the same time. So supersolid is a paradoxical quantum fluid with the frictionless flow of a superfluid and a crystalline order of a solid. So what happens when you have an order in a solid? So in liquid and gas, so it's all uniform. So whichever direction you try to go, you find that it's same everywhere. So there is no breaking of continuous translation and symmetry. But in crystalline solid, it's not the same at every point in space. So there is actually breaking of continuous translation symmetry. So this is the concept which we need to understand in supersolidity. So in a supersolid, you have, without any underlying periodicity, you have the Bose-Einstein condensate getting arranged in a form of a regular pattern because of the formation of supersolid. So here you can see in this video. So it starts from no periodicity, and then it gets arranged in a periodic pattern, which is the supersolid pattern. Okay, so now I come to the last part of the talk, quantum technology with cold atoms. So quantum computing or quantum technology, the concept started way back from Richard Feynman, who suggested that quantum simulator is where one controllable quantum system simulating another. So to have quantum simulation, we use what is called an optical lattice. Now, what is an optical lattice? So if you have a laser beam and you retroreflect it, you have a standing wave pattern. And you can actually trap atoms in this standing wave pattern. And so this will actually emulate electrons in a solid state system. So quantum gases or Bose-Einstein condensate in optical lattice, it emulates electrons in a solid state system. So it's like a quantum simulator. So in an optical lattice, you can control anything, all the parameters, just like in numerical simulation. You can control the dimensionality, you can control the lattice geometry, the tunneling between the lattice sites, the interaction, everything. So you can also go to any parameter range and you can explore new physics. You can have change the lattice geometry, you can make any kind of lattice geometry and trap the atoms in those kind of atomic geometry. So if you have a 1D optical lattice, you can form an array of 2D geometry. If you have 2D optical lattice, you can form 2D array of 1D geometry. And if you have a 3D lattice, you can have an array of points in space. So there are a lot of quantum simulation experiments which has been done with atoms in optical lattices. And these are great advances which has been done in this field. So we have seen children playing with Legos. So with few pieces of Legos, they can build wonderful structures. So in the same way, using this optical lattices, with atoms in this optical lattices, we can make any kind of configuration. We can explore the physics of materials by arranging these atoms in various configurations in this optical lattices. And we can look at quantum magnetism. We can look at open questions in high temperature superconductors. We can also try to answer the question that is it possible to make a material that is superconductor both at room temperature and atmospheric pressure, which is still the holy grail in physics. You can use this atom synoptical lattice as atomic Legos to answer these open questions in physics. So quantum technology. So quantum technology is the acquisition, storage, transmission, processing of information using quantum sensors, processors, and transmitters. Now, quantum technology has 4 different regimes: quantum computation, quantum sensing and metrology, quantum communication, and quantum simulation. So I come to the final part of the talk where I talk about the quantum technology experiments which I do with Rydberg atoms at Raman Research Institute. So Rydberg atoms are atoms with electron at very highly excited state, and so they are at such a highly excited state that the size becomes very, very large. So generally atoms are like size of angstrom, but in Rydberg atoms they can be so large that they can be of the size of a human hair. So these are large atoms which are the giants of the atomic world. So Rydberg atoms was discovered by Johannes Rydberg way back in 1888. So he had found the empirical formula linking the various wavelengths of the spectral lines observed in alkali atoms, and this played an important role in the birth of quantum mechanics. So Rydberg atoms with electron at very highly excited state, they get very exotic properties. They have very large size, as I just mentioned, and they have very long lifetime. So this gives them very long coherence time, which is very important for quantum technology applications like quantum computing. And they have very large interactions. So they interact very strongly among themselves. So if n is the principal quantum number, that means it characterizes the electronic state to which it is excited. So the larger the principal quantum number, larger the interaction and larger the lifetime. And it has very large polarizability. That means, which goes as n to the power 7. That means it's extremely sensitive to external electric field. That a very small electric field is enough to create response in this Rydberg atoms. And it has very large interatomic interaction like the dipole-dipole interaction, and very large van der Waals interaction, which goes as n to the power 11. So you can see a very strong dependence on the principal quantum number, so it's very strongly interacting. Now, this strong interaction between Rydberg atoms has a very important consequence, that you can create quantum entanglement using Rydberg atoms. Now, if you can imagine there are 2 atoms which are very far apart, they are not interacting. Now you bring one of the Rydberg atom closer. So because of this very large interaction, their energy level shift of the other atom, because of the interaction, it causes an energy level shift in the other atom. So if you have a laser beam which excites one atom to the Rydberg state, it cannot excite the other, and vice versa because of the energy level shift. So you can see there's a correlation which is formed between these 2 Rydberg atoms, and this correlation leads to the entanglement, generation of entanglement between these 2 Rydberg atoms. So this is the basis for making quantum gates or quantum computation with Rydberg atoms. So the quantum entanglement is at the center stage, which is evident from the fact that the Nobel Prize in 2022 was awarded to Alain Aspect, Jean Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So this is our group at Raman Research Institute. So this is our experimental group. I have 5 PhD students and 1 project student from ISRO. So here you can see that there's majority of women. We have women power in our group. And we have theory collaborator from RRI, Shobhan Datta and Rajesh Nath from ISR Pune. So this is our experimental setup, and we have the cold atoms, the vacuum chamber, which we produce here. So here we use a 2-step process for the Rydberg excitation from the ground state to the excited state. So first we excite from the ground state to an intermediate state using 1 laser, and another laser which we call the Rydberg laser. We excite from the intermediate state to the Rydberg state. So this is the signal from the cold Rydberg atoms. So in our experiment at RRI, this is the first and the only cold Rydberg atom experiment in the country. So the next step in this experiment is to trap single or individual Rydberg atom in optical tweezer. So for this, we focus the laser beam to extremely small focal point, like 1 micron. So at very small focal point, it will ensure that either there is 0 or 1 atom in the optical tweezer, because at such a small volume, if there are multiple atoms, they will collide and both of them will go out of the trap. So this small focal spot will ensure that there is single atom or 0 atom in the optical tweezer. So we have lens inside the vacuum chamber to create that optical tweezer for single atom trapping. So what's the use of single atom trapping? The ability to trap individual atoms allow controlled engineering of the quantum state. The single quantum system necessary to encode and process information at the quantum level, and to explore quantum physics of particles at the microscopic level. So the importance of addressing microscopic or individual particles was recognized in 2012, where Serge Haroche and David Wineland were awarded jointly the Nobel Prize for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. So the idea in the experiment is to have this optical tweezer, an array of optical tweezer with individual atoms trapped in this optical tweezer, and then excite them to the Rydberg state. And as I had explained a few slides ago, create quantum entanglement between them and create quantum entanglement and have individual Rydberg atomic qubits and realize a quantum network of this Rydberg atomic qubits to work towards building an array of Rydberg atomic qubits to create a quantum network and eventually a neutral atom quantum computer. So we all know that in microscopic level, it follows single particle physics. And in the macroscopic level, in the real world, it follows many body physics. But what happens in between, in between the microscopic regime and the macroscopic regime? So there is a very interesting mesoscopic regime, and Rydberg atoms are just in the Goldilocks regime, where it can explore this mesoscopic regime. So the idea is to have atom by atom assembly of this Rydberg atoms, and then go from a microscopic regime to explore this mesoscopic regime and explore the scalability to build a large 1D or a 2D array of this scalable quantum network. We can also arrange this individual Rydberg atoms in a triangular or a square array and look at antiferromagnetic ordering with this Rydberg atoms in this triangular or square array of optical tweezers, and look at open questions in quantum magnetism. So we can have this Rydberg array of Rydberg atoms in a disordered potential and look for new quantum phases. And we can do quantum sensing and metrology with Rydberg atoms. As I had said, Rydberg atoms, since the electron is so away from, far away from the nucleus, it's very sensitive to external electric field. So it can sense very, very small electric fields. It can be also used for example, sensing electric pulses or from brains, and also like looking for minerals deep down in the earth. So all this are makes Rydberg atoms very promising for quantum sensing with Rydberg atoms. So we can choose various kinds of energy levels, and we can use Rydberg atoms to have do quantum sensing of microwave or terahertz radiation. And we can use Rydberg atoms, single Rydberg atoms, and use it as a very highly sensitive quantum sensor to sense both DC and AC electric field. We can also try to beat the standard quantum limit via quantum tricks such as squeeze states, and reach the Heisenberg limit, which is the holy grail of quantum measurement. So I come to the final slide of my talk. So this is the summary. I gave an introduction to Bose-Einstein condensate and how we realize it in the laboratory. I talked about exotic properties of Bose-Einstein condensate like superfluidity and supersolidity. And I talked about quantum technologies with Rydberg atoms and future perspective on quantum information and quantum sensing with cold Rydberg atoms. Thanks for your kind attention. Yeah.
Ma'am, so now that we're towards quantum sensing, and you mentioned that like it can sense materials quite easily. So what if we were to industrialize this technology?
Yeah.
And ahead of that, there are many other parts of quantum technologies as well, like quantum computing, simulation, and everything. So just like if sensing were to like be industrialized, how would it affect us? And furthermore, if other quantum technologies could be industrialized, how would it affect the present industries and our day-to-day lives?
Yeah, so actually there have been several companies, one in France and one in started at Harvard University, which is actually doing it's actually commercializing. It has started a company which is actually making quantum computers with Rydberg atoms. So, which is a company for neutral atom quantum computing with Rydberg atoms. So it has the effort has already been started. So hopefully we can also have such commercialization in India as well with Rydberg atoms.
Hello. Yeah. So I had one question that how do we know that the atom is trapped in optical tweezer?
So we can actually detect them. So we have a very sensitive, two sensitive detectors. One are cameras, which is actually focusing exactly at the point which is atom supposed to be trapped. If you don't see any signal, there's no atom. If you see a signal, that means there is atom. And you have also something called a avalanche photodiode, single photon detector module. So if you have a signal in that, you know there is an atom. If you don't see a signal, you know that there is no atom. So,
And like how do we entangle them after they are trapped?
okay, so we use laser pulses. So when we use the internal states of these Rydberg atoms, and we map these states which we can recognize by detecting them. So if we so we have this two hyperfine ground state. So if you have atoms in the upper hyperfine ground state, that means it has not gone to the Rydberg state. And the Rydberg state is mapped to the lower hyperfine ground state. If you see it in the lower hyperfine ground state, you know it has gone to Rydberg state. If you measure these atoms in these states, you know it has gone to the Rydberg state or not. So by measuring, you know how much is the fidelity of the entanglement. That means how much the entanglement has happened. So by making this measurement, we know that the quantum entanglement has happened.
Okay, thank you.
Ma'am, can you show the slide for optical molasses?
Yeah. Yeah.
Ma'am, here we are giving laser, we are giving laser beams to the particular atom from all the three, from all directions. You're saying, but won't it like cancel the effect of each other laser beams?
Sorry?
Like, see, like you told, like there's an atom here, and then we are pointing a laser here, and they're pointing a laser another here. Won't it cancel the effect of those two lasers?
No,
'Cause
it's
it's
not
just
cancellation of effect.
okay.
It's like cooling in this direction.
Okay.
So when you have lasers in all three dimension, so all the three dimension cooling is taken care of. It's not, it's cooling in the three dimension.
Another thing that you mentioned about the vortices of how the vortices of Bose-Einstein condensate. Is it like this Bose-Einstein condensate, when we just rotate it, you said that it forms vortices, right? Is it because like there's a creation of mini whirlpools that is leading to this creation of vortices?
Sorry?
Whirlpools, we are whirlpools.
Yeah, you can think like that, yes. So it's like, so as I said, it's because the velocities cannot take continuous values. So that's why it's giving rise to the vortices, because the matter wave has to, close upon itself, right? So that's why the velocities cannot take continuous values. It can take only quantum values. So that is giving rise to these vortices.
Is it possible to perform single atom trapping for particles smaller than the Rydberg atom?
Yeah. So the idea is to first trap a single atom in the ground state and then excite to the Rydberg state.
Yeah, so I wanted to ask, can you give a brief about supersolidity, and then how does supersolidity and superfluidity coexist in the Bose-Einstein condensate?
So it's a special, okay, I'll show you. So it does not happen in all Bose-Einstein condensate. You need to create special conditions in the experiment to do that. So individually, these different, different parts you see, they are individually superfluid. If you rotate each of them individually, you will find vortices. Now, the supersolidity, it comes from the fact that it starts from no periodicity in the system, but the condition that in the experiment has been created in such a way that it forms regular pattern. It arranges itself in the regular pattern like a solid state. So this is the so this coexistence of the superfluidity, which is the individual of them, and this regular pattern, so that is the supersolid behavior. So this coexistence make them supersolid.
Like we are talking about the Rydberg atoms, and the entanglement of the Rydberg atoms, we are having qubits from them. So in the Raman Research Institute or TIFR, how many qubits are we able to realize the entanglement of how many qubits?
So right now we have built, so what we have done is we have created the optical tweezer. We have made it ready. So we could already create an optical tweezer of which less than 1 micron focal spot. So which has prepared it for trapping a single atom. So our next step in the experiment would be to trap the single atom and then excite it to the Rydberg state and create entanglement and then create Rydberg atomic qubits.
Can I ask one more question?
Sure, sure.
Yeah, so I wanted to ask, like, there are some other methods for quantum technologies, like topological insulators, other than the ultra-cold atoms, which we can realize quantum technologies. So what are the particular advantages of ultra-cold atoms over the other methods of quantum technologies?
So ultra-cold atoms, one advantage of ultra-cold atoms is that the temperatures are very low and the quantumness is inbuilt. So as you saw that, lower you go in temperatures, the de Broglie wavelength increases and you automatically go in the quantum regime. So you don't have any decoherence due to thermal effects because it's already very cold. And since being neutral atom, unlike other systems where there could be large Coulombic interaction, these are neutral atoms. So you don't have decoherence due to external fields. So these are some advantages. And you can have very high degree of controllability. As I said, you can control any parameter, just like in numerical simulation, you control any of the parameter. In the experiment, also you can control any parameters. Very high degree of controllability. It's like numerical simulation, but now the simulation, you do quantum simulation on real atoms. Okay, so this is the advantage of cold atoms.
Can you explain about which elements can be used at Rydberg atoms and the size criteria is very necessary or not? Can a small atom with only one electron, which is in very high energy, can it also be used as a Rydberg atom?
Yeah. So you can have like we use rubidium atoms, but many kind of Rydberg atoms are there, like potassium, strontium. So many groups have created Rydberg atoms in different kinds of atoms. So it's not sacrosanct that you have only one kind of Rydberg atoms.
Ma'am, can you also explain about ion trapping?
Yeah, ion trapping, of course, it's not my field of research, but ion trap is where you have ions and you have very strong electric field. And because of this electric field, the ions get, trapped because of this, potential created by this electric field. So this is ion trapping. So, which you cannot go as low in temperatures like in atoms.
Ma'am, can we like how we do with other physical states of matter? Can we like touch and feel both?
Unfortunately not, because I showed you that it's in a vacuum chamber where the pressure is 100 billion times lower than the atmospheric pressure. So you definitely cannot touch it. but you can see it with a camera or.
Like, could we like one day hope to bring it to like a normal environment?
Yeah, probably you can have a BC machine. Yeah, a small miniaturized VC machine. Yeah, people have made this miniaturized VC machine. It's possible. Yes, a small size of this box, kind of. Yes, you cannot touch it for sure anytime. Yeah, optical potential. This one. Okay, so this is optical dipole trap. Now, what happens is if you have a laser beam, a very high power laser beam, and you focus it to a point, uh, and then you create a intensity pattern. So the profile is Gaussian, the intensity profile is Gaussian for the laser beam. If you focus it, you will have a profile of the intensity like this, okay? Now, so this, the frequency of this laser beam is very, very far away from the atomic transition frequency, okay? Now, the atoms interact with this laser beam using what is called a dipole force, which is the D dot E force. That you understand? Okay. Suppose you have an electromagnetic field. Okay. So in the electromagnetic field, there's an oscillating electric field. And you can think atom as a dipole. Okay. So this oscillating electric field creates an induced oscillating dipole moment in the atom. Now that induced oscillating dipole moment interacts with the electric field to have this D dot E force. Okay, and so that D dot E force that creates that dipole force. Okay, now electric field, so the larger the intensity, that means larger the electric field. Okay, so larger the force. Okay, now if you have focus it, so at the focal point, the intensity is maximum. So the force is maximum. The atom gets attracted to the maximum intensity. So the atom gets trapped to that maximum intensity point, so which is the minima of that potential. Okay, so that is the optical dipole trap.
Ma'am, since all these phenomena are happening at like almost absolute zero, will we have to um, operate quantum computers at that temperature?
It's not absolute zero. So BC happens like in nanokelvin temperatures. For Rydberg atoms, we can do even at microkelvin temperatures. So yeah, we need to have the lab conditions in those, in microkelvin temperatures at least. We need to maintain that. Yes.
Hello. Ma'am, I wanted to ask a question about these whether beams and atoms are getting trapped in those beams. So, can we also use it for molecules and maybe apply it for catalysis of chemical reactions?
Yeah, probably. Yeah, molecules have also been recently been trapped. There are several groups. I know of a group in NIST and also in Stanford who trap molecules, and also in Florence they're trapping molecules. Yeah, you can use molecules and also do quantum chemistry with molecules.